Alright, this video is on effective nuclear charge and the shielding effect. Before we get too far into what either of these things are, we need to first define what nuclear charge is, because that's going to help us understand shielding effect and the effective nuclear charge. Now, both of these are important for our periodic trends, such as ionization energy, the atomic radius, and then later on, the electronegativity trends on the periodic table. So before we get too far in, like I said, we're going to talk about what nuclear charge is. Now, nuclear charge is directly related to the number of protons, okay, that are found in the nucleus, right? So I have, say, 10 protons, and that is going to result in, say, a higher nuclear charge than if I only had 5 protons. So here I have my protons, and the nuclear charge, right, is based on the attraction that those protons have with the electrons that are in the orbitals, whether they be core electrons or whether they be the valence electrons. All right. So just a little diagram right here. What I have is a variety of different Bohr models of atoms. Okay. This right here is our first period, second period, and third period. And then I have some main group elements. This is the first main group element. This is the sixth main group element, the seventh main group of elements, and then the eighth main group of elements. Remember, the main groups do not include the transition metals. That's why the carbon family is considered the sixth main group element, or main group of elements. Okay? So I want to take a look at nuclear charge and what that means. So I'm looking at, say, hydrogen. There's one proton in hydrogen. I'm looking at lithium, right? There's one proton in lithium, okay? So I am here, right, of hydrogen, lithium, and sodium. Those are the three that I'm looking at. Well, as I go down a group, okay, as I go down my column, my nuclear charge is increasing because my number of protons is going to increase, right? So the trend for the nuclear charge increases as you go down a group. And then if I look from right to left, going from, or excuse me, not right to left, but going from left to right, okay, my nuclear charge is also going to increase because as I go from left to right, the number of protons is going to increase. So if I look at my, say, my second period right here, okay, I look at my second period, as I'm going across the period from left to right, the number of protons is increasing. Well, with the number of protons increasing, that's also going to mean more nuclear charge. All right? So now that we have a good idea of what nuclear charge is, what I'd like to talk about next is effective nuclear charge, which is, like I said, draws on the same basis, but we are going to be taking a look at a particular type of attraction between the protons and electrons, or specifically a particular type of electron. All right? So, an effective nuclear charge, okay, so now we're talking effective nuclear charge, is actually based on the protons that are in the nucleus and how they are interacting with the valence, or how they're attracting the valence electrons. Okay, not just the core electrons, but and the valence electrons together, as we did in nuclear charge. But now this is this is just the valence electrons here. Okay, and there is a formula that's pretty straightforward. Okay, the effective nuclear charge, okay, which in this case we just call F. Okay, effective nuclear charge, or let's go ahead and just call it ENC, just so we can keep our acronyms nice and easy. Right? So the ENC, the effective nuclear charge, is going to be equal to Z, which is the atomic number, so the number of protons, minus the number of core, that's horrible, number of core electrons, right? So you're thinking, well, how do I determine the number of core electrons? Well, that's what we have the electron configurations for. Okay, if we have the electron configurations, then we know how many core electrons we are, because we should be able to determine the number of valence electrons that an atom has. All right, so let's go ahead and shoot back forward here, and let's take a look at. Let's go ahead and we'll key on carbon. Right. So I'm going to go ahead and go forward. Here's carbon. Carbon has 6 protons and, let's go ahead and go black. 6 protons and 6 neutrons, so this would be an isotope of carbon 12, right? 12 and 6, right? There's the isotopic notation. And then let's go ahead and take a look at the electrons. I have 6 electrons. I have 1, 2, and then 3, 4, 5, and 6, right? I try to keep those electrons as far away from each other as possible. Now, with my 6 electrons, I am looking at the valence number of electrons, okay? So I can determine my effective nuclear charge because I need to know the number of core. Now, of course, you can always draw out a Bohr model and then count the number of electrons that are in the core and then go from there. But what I'd like you to be able to do is use the ground state electron configuration, right? The 1s2, 2s2, that kind of stuff, to determine the number of core electrons so you can calculate the effective nuclear charge. So if I have, say with carbon, that would be 1s2, 2s2, and then 2p4, right? So, excuse me, 2p2, my bad, 2p2. Okay, so looking at that, identifying my number of valence electrons is going to be looking at how many electrons do I have in the outermost energy level. In this case, the outermost principal energy level is going to have 4 electrons. I have 2 here and I have 2 here, so the valence electrons is equal to 4 electrons, okay? Which means if I want to know the number of core electrons, there's obviously 2 ways I can go about doing this. I can count all the electrons that are not valence electrons, so 2, right? Or I could say, all right, well, there's 6 total electrons, and then I have 4 valence electrons. I subtract, I should end up with 2 core electrons. Okay? So that would be the number of core electrons I have. Now you're thinking, well, what does that mean for my my effective nuclear charge? And what I'm going to do with, say, carbon, like I said, is there's 6 protons, okay? And I have, come on, there we go. And I have 2 core electrons. That means I'm going to go, my effective nuclear charge is equal to Z minus the core electrons. So that would be the same thing as 6 minus 2. My ENC for carbon atom is 4. Okay? So, and what this effective nuclear charge means, there's a variety of different ways that we're going to be using effective nuclear charge, but before we use it, I need you to know how to calculate it. All right? So, obviously, the more core electrons you have, right, that's going to affect the effective nuclear charge. All right? So, oops, no, don't want to go there yet. So let's go ahead and go back. I'm going to do a little erase job here. All right. Okay. Go back here. And here. Okay, so now that we know how to do the effective nuclear charge, okay, let's actually see what we can do with it, or how we can predict how it affects the how it's going to affect the periodic trends, such as ionization energy or atomic radius. Okay. Now, when it comes to ionization energy, all right, I'm going to go ahead and pick. Since we already did carbon, I'm going to pick on these 2 right here. Okay. Carbon and fluorine. We already know what carbon's effective nuclear charge was. It was 4. Okay. Now, the effective nuclear charge for fluorine is going to be a little different, okay? Because I have, if you look, obviously it's a little easier to see since we already have the Bohr models drawn. I have 1, 2 core electrons there, and that means I have 1, 2, 3, 4, 5, 6, 7 valence electrons, so all the math works out. Well, in this case, I'm going to end up doing my equation to be 9 minus 2, because I have 9 protons and I have 2 core electrons. So my effective nuclear charge is 7 for chlorine, right? Or sorry, excuse me, for fluorine, my bad. Which hopefully we see that as we go across, Okay, if we go across the period, my effective nuclear charge is going to increase. All right, and that's even going to be true when we get into um, some, even in noble gases, my effective nuclear charge is going to go up to 8 with neon. So my effective nuclear charge is going to increase as I go right to left. Now you're thinking, well, what does that mean? What does it mean that I have a greater effective nuclear, or a greater nuclear charge, or a greater effective nuclear charge, right? So let's go ahead and, like I said, take a look at ionization energy. The amount of energy needed to take a valence electron away, okay? Well, the more um, you have of an effective nuclear charge, the higher your effective nuclear charge is, the harder it's going to be to um, pull that electron away. Okay, so if we look at fluorine and we look at carbon, right? Carbon has 4 effective nuclear charge. Fluorine has 7. What does that mean? That means that of all these valence electrons, okay, they have a strong attraction to that nucleus, to the factor of some arbitrary unit, 7. Okay, these valence electrons in carbon also have an attraction, but the effective nuclear charge is actually less. Because that effective nuclear charge is less, it does not take as much energy to remove that electron, and that's why our ionization energy is increasing as we go across our period. It's because our effective nuclear charge is increasing as we go across our period. All right. So if I was to change things up a little bit, and we'll still stick with carbon because carbon's our friend, right? Let's go ahead and look at carbon and silicon, right? So you're thinking, well, what's happening here? Because now my effective nuclear charge going to make a difference? Well, here the effective nuclear charge for carbon isn't going to change. It's still going to be 4, okay? Right? But now with silicon, it's a little different because I have 14 here, okay? And if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait a minute. This is looking somewhat familiar because if my effective nuclear charge, if my in the same family, in the same column, if I have the same number of valence electrons, okay, then shouldn't that mean that they're going to be acting acting the same? And in truth, they don't, right? So what I mean by that is here I have 14 protons, so I'm going to go ahead and do the math right over here, right? So I have 14 protons, and I'm subtract that from the 10 core electrons. Okay, so because I have 10 core electrons because I have 4 in the valence. So 10 core electrons, and you're going, well, the effective nuclear charge is 4. Okay, the reason why I'm showing you this is to let you see that effective nuclear charge really does not have an effect on on 2 elements that are in the same group. Okay, so I mean for the confines of our class, if you notice that the effective nuclear charge really isn't changing because I have 4 here and I have 4 here. So what I want you to realize is the effective nuclear charge is not going to play a part in determining any periodic trend for elements that are in the same group. Okay, so let's go ahead and move. Let's do some erasing here. Okay, and we're going to go back to our first slide where I now want to talk about shielding effect and how shielding can play a role in atomic radius and ionization energy. Okay, so and of course there is, I'm sure you guys can discern, there is a connection between effective nuclear charge and shielding effect when we get to shielding effect, which is right now. But mainly, I don't need you to see the connection between those two. If you do, great, right? But if you know effective nuclear charge and how to calculate it and how it affects things like ionization energy as you go across a period, good. Shielding effect, along the same lines, but in this case, shielding effect doesn't really play a big role going across, but it does play a big role going down a group. Okay, so let's go ahead and hop over to this slide right here. All right, so these electrons right here, this picture, I have 2 different types of electrons. I have valence electrons. Here's a valence electron, here's a valence electron. And then I also have some core electrons. Here's a core electron, here's a core electron, and here's a core electron. Now, just knowing how, and of course our nucleus, which is right here, okay? Now we know how um, electrons interact with the nucleus, right? They're attracted to it. But we also know that electrons are also going to interact with each other, and they're going to repel each other away. So what does this mean, or what's my MO right here? Well, this process of the valence electrons, these guys right here, being attracted to the nucleus, and honestly, this is somewhat inaccurate because these guys are also attracted to the nucleus. I should go blue, I guess. You know, these guys, these core electrons, are also attracted to the nucleus, but I think they just save the room, okay, on the picture. But the valence electrons, they're attracted to the nucleus. However, they're also being repelled by these core electrons. And it's actually pushing this valence electron out a little further, and this repulsion, because this valence electron is pushing back on that core electron, the core electron's actually getting closer to the nucleus. Okay, so as we are getting, if I have these valence electrons right here, okay, they are repelling the core electrons, and the core electrons are repelling them, so they're getting farther out, and then the core electrons are now getting closer. And you're thinking, well, what does that mean? What does that have to do with anything as far as like the ionization energy? Well, if you think about it, the farther out that valence electron is away from the nucleus, right, then the lower, essentially, right, the lower the effective nuclear charge, which means this nucleus can't really hold on to that valence electron that much. And when it can't hold on to that valence electron that much, then it could possibly just give it away. And in doing so, we lose that valence electron. So the atoms that are most likely to do this, that like to get rid of electrons, such as metals, okay, especially the alkali metals and the alkali earth metals, right? The interaction between these core electrons and the valence electrons is called shielding. It's a shielding effect, where the core electrons are pushing away the valence electrons, and because they're being pushed away, right? Because they're being pushed away, they're not being as attracted to the nucleus, and when they're not being as attracted to the nucleus, then it's easier to take them away from the atom. Okay, wherefore it's easier to form an ion. That's why you have lower ionization energies for elements that will shed an electron. Okay, so let's go ahead and do a quick comparison here. All right, let's look at a group and a column. So let's go ahead and pick on these guys here, and we'll pick on these guys here. Okay. Now, first we'll pick the period. Okay. Or no, that's not. Let's pick the group first. So we're picking the group. What's happening as I go down my family? What's happening if I go down my group? My number of core electrons is increasing. Okay. Well, important. Write this down. As the number of core electrons increases, the amount of shielding also increases. So if you were to say which of these three elements is experiencing the greatest shielding effect, the answer would be sodium, right? Well, if it's experiencing more shielding, then guess what? It's going to be pushed away from the nucleus more, and when it gets pushed away from the nucleus more, that means the nucleus isn't holding on to it as tightly. And when that nucleus isn't holding on to it as tightly, it's easier to have that electron leave and be picked up by something else. Okay? This is why as you go down a group, the ionization energy is going to decrease, because it's not taking as much energy to take that electron away, and the reason why is because that electron is farther away. And you're going to be thinking, well, also, I just have more energy levels, and the more energy levels I have, the farther away it is from the nucleus. True, that is playing a key role, but it's even getting an extra oomph away from the nucleus by those core electrons shielding it from the nucleus. And the more core electrons you have, the more shielding you'll have. Okay? Now, that's it for the group, right? So we understand the relationship between the the group and shielding effect. Now let's take a look at the period and our shielding effect. Okay, what did I say? The more core electrons you have, then the stronger the shielding effect. So looking at lithium, carbon, fluorine, and neon, what do you notice? Okay, hopefully you're not thinking, oh look, eyes on a smiley face. You're going, the number of valence electrons, the number of core electrons is the same as you go across a period. And it's because the number of core electrons is the same that shielding effect does not play a big role as you go across a period. Okay? So if you looked at before, we looked at effective nuclear charge, right? The effective nuclear charge was playing a role as we go across a period, right? That's effective nuclear charge. Well, as you go down a group, right, that was shielding. Okay? So keep that in mind. As we're going across a period, shielding does not play a role because all the valence all the core electrons, they're the same number of core electrons as you go across. So it's not playing a big role there. Okay? And then the effective nuclear charge is playing a role as you go across because as I have the same number of core electrons, but my number of protons is increasing as I go. Okay? There are some minute differences here in the fact that the effective nuclear charge does in fact change as you go down a group. Okay, and in fact it's actually decreasing, but that's beyond the scope of the course, and so we're not going to worry about that. If you have any questions, by all means ask, and I'll see you in class.